Well, good afternoon, everybody, and welcome to the MTL seminar series. And we're going to start this term with a very exciting presentation. I mean, very close to my heart because I'm one of these MEMS guys, but Dr. Fadi Alsaleem doesn't do your standard MEMS. Well, for people who don't know, it's microelectromechanical systems, so are these devices that do this pairing between different energy domains, perhaps sensing, actuation, etc. So we're very fortunate to have him here. He's a professor from University of Nebraska at Lincoln, and he has this extensive industrial experience, and also he has been heavily funded by various agencies to do this work that, for lack of a better word, we should call it like analog computers. So he's going to tell you a lot more about that. So thank you again for coming, and we're eager to hear your talk.
Thank you for the nice introduction, and thank you for the invite to give this talk. So yeah, my talk is about non-conventional MEMS, like a new way of doing MEMS, like conventional MEMS doing sensing. For the first time, we try to do blend sensing and computing in one application. So I've been thinking with my students, like I have 5 grad students, which I will share next year. So this is kind of, I always try to acknowledge my student because most of the work is done by them. And one thing unique you will see, like, since my work is kind of multidisciplinary work, they come from different backgrounds: mechanical engineering, computer engineering, electrical engineering. And that's kind of the skill you need for such kind of a big project like this. And also, I would like to acknowledge my collaborator, Dr. Borkomoli from UT Dallas, to do the fabrication. Dr. Rosby, he used to be in Texas A&M, and now he moved to MIT Lincoln Lab, and GE and other faculty from other universities. So as I mentioned, I was struggling to how the best way to present my work in a nice way. And you will see I talk slow, I talk fast, my English is not good, so I thought maybe let's make some automated video that can describe the motivation and the innovation of this work. So this is kind of quickly we put it together with my students. So I hope it conveyed the idea about the challenge we try to tackle with this approach, and then I go in more technical details. So please enjoy this video.
In today's world, the Internet of Things, IoT, is transforming our lives. It's reported that by 2025, IoT devices with billions of sensors are expected to generate 175 zettabytes of data, presenting significant challenges in data management and processing. Current digital computing technologies are increasingly energy-hungry and face limitations in handling the overwhelming flood of data. These technologies aren't keeping pace with the growing demands. In a typical data processing pipeline, the process begins with sensing. After sensing, the data goes through conditioning, analog to digital conversion, computing, and finally, output delivery. During the computation stage, once the data is prepared, it can be processed locally using a computer or microprocessor, or it can be transmitted to the cloud for online processing, where the output is then received. When comparing these methods, local processing is often slower and consumes more energy. Cloud processing, on the other hand, offers faster speeds and generally lower processing energy costs, but it comes with the added energy and complexity of data transmission. In both scenarios, computing energy consumption remains a significant challenge, while sensing itself doesn't pose a major energy problem. So, what if we could utilize our low-energy sensors as processors? Traditionally, sensing has been separated from computing in digital processing methods. Sensing is from Mars and computing is from Venus, 2 separate worlds. But when you bring them together, you create VenuMars. At the new MEMS lab at the University of Nebraska-Lincoln, we're pioneering MEMS sensing computing. We're exploring new methods to process data directly at its source by merging sensing and computing into one seamless process. MEMS, microscale devices that have found their way into everything from smartphones to space shuttles. MEMS stands for microelectromechanical systems. An example is the MEMS accelerometer. A MEMS accelerometer functions as a variable capacitor. When acceleration is applied, it changes the distance between mechanical structures, altering the capacitance and generating an analog voltage that represents the applied force. Because a MEMS sensor operates as a capacitor, it consumes very little power, with no current flowing through the sensor itself. Its small size and low cost make it highly advantageous. MEMS technology also includes devices like gyroscopes, pressure sensors, and microphones. But our new MEMS devices go beyond these roles. They both sense and compute. We've advanced MEMS technology by creating a network of these sensors that work together. Instead of relying on external computing, our MEMS network processes data in real time at the source. Our new MEMS network, short for Neuromorphic Edge-Aware MEMS, features innovative designs like the RC series for reservoir computing, the CS series for combined computing and sensing, and the C series for computing only. These designs can be mechanically or electrically coupled and come in various stages. They are highly configurable, allowing for adjustments in sensitivity or frequency. Additionally, they incorporate adjustment plates for real-time tuning using electrical voltage, enabling precise fine-tuning of both sensitivity and functionality. This flexibility ensures seamless integration of sensing and computing within the sensor itself. In nature, we find inspiration from small creatures like insects. Despite having only a few 100,000 neurons, insects can often outperform humans, who possess billions. Unlike humans whose neurons are primarily concentrated in the brain, insects have neurons distributed throughout their sensory organs. This decentralized neural network allows a bee, for example, to navigate miles away from its hive and still find its way back, while we often lose our sense of direction within just a few blocks. Inspired by this natural efficiency, our new MEMS devices bring neuromorphic computing directly to the sensor level. The potential applications of this innovation are vast. For instance, our sensors can distinguish between activities like walking and running and can detect falls in real time. With their ultra-low power consumption, these sensors can operate for years on a single battery charge, making them ideal for long-term monitoring solutions. Another application of our new MEMS is bridge health monitoring. Many older bridges are approaching the end of their healthy lifespan, yet fewer than 100 are actively monitored due to the complexities involved. Our MEMS sensors provide continuous, on-the-spot monitoring, enhancing safety while reducing long-term maintenance costs. Beyond previous applications, our reservoir computing MEMS enable rapid, low-cost detection of peripheral artery disease, PAD, while our computing MEMS handle high-speed signal processing. These innovations enhance diagnostics and data analysis efficiency, and the possibilities are limitless. Any innovative application can take advantage of our technology's benefits: speed, configurability, power efficiency, advanced sensing capabilities, efficient data processing, and scalability. With these features, we're not just creating new solutions, we're pioneering the next era of technology.
Kind of give some information about this technology, and I'll try to dive more details in the technical. So I thought this is kind of give you some background about the work we do, why we do it, and where the application. But as you can tell from this short video, right now there's a lot of data outside, like from IT device, Apple Watch, your smartphone, and there's a very major challenge with that is. As the video shows, there's kind of the sensing computing. They never meet each other. They're completely different world. And because of that, they didn't speak the same language. So we're wasting a lot of energy and resources to make them talk to each other. To give you a perspective, the sensor itself, it's a MEMS device. It consumes very much power. Most of the power is being consumed to do the ADC, the processing, the communication. And you can see there's a lot of security going there to make them talk to each other. On top of that, we're still using digital computer. As you know, like we're approaching the Moore law, where when you start talking about machine learning, digital computer are not the optimal way to do computing. So we have two challenges coming together. The complex interface between the sensor and computer, and the computer is still using the digital computing approach that separates between memory and processing. Yet the clue here is the sensor itself consumes the least amount of power. So how we can capitalize in this? So this solution didn't come overnight. I've been working this idea for many years. So to the left here is, again, the conventional MEMS we talk about in the video. You have a sensor. The sensor produces a voltage. Then the voltage, you need to condition it so you can high amplify it. And then the fact our computers are still digital, you want to do ADC, which consume a lot of power, by the way. And then at the end, want to send a microprocessor to do the computing. So in my PhD, I said, can we solve a small problem from that? Can we realize a MEMS that can do sensing and actuation? So we realized a very simple switch, a switch that we trigger by if the measurement of interest, like acceleration, exceed a threshold value, then utilizing the nonlinear dynamic of the MEMS will collapse and produce a switch as an on. If not, will be off. With this solution, it's a very simple solution, but we're eliminating all this ADC and microprocessor. But the major issue with this is only magnitude, on, off. But you know, in real life, there's a very complex scenarios. Think about the fault detection we mentioned in the video. Yeah, magnitude is part of it. If somebody's falling down, we'll have high G. But sometimes you might throw yourself on the couch. You don't want to trigger this to be a fall. You need to look at what happened before, what happened after. And now you start kicking the machine learning. Okay? So one step before jumping to this MEMS sensing computing, in parallel, my collaborator, I was not aware of that, but when I was doing my work, after I got to know him from UT Dallas, I realized, and Dr. Rosby from MIT now, they're doing something interesting in the middle. They, for the first time, bringing those MEMS switch, they connect them in a linear fashion, and the output of those switch will convey a binary code of the applied acceleration. So what this means, if there's acceleration applied to those switch, they arrange them in a way, based on the magnitude of the acceleration, some of those switch will be on, some will be off. And that will give us the binary code. So they skip now, they eliminate the need for the ADC. They don't need to worry about sampling the sensor. But the issue is still yet, you need a microprocessor to process the data. So now the solution we're working on now, for the first time, we're building a whole network from those MEMS, and we engineer each MEMS to act as a neuron in the typical machine learning. What we gain from that? First of all, those will be analog. So they will do computing on the fly. And most importantly, those are sensors. Still, they are sensors, so they react to the environment, sense our measurement of interest, but at the same time does the computing. So eliminating all this layer of ADC, conditioning, and even the need for microprocessor to do this functionality. So that's kind of summarized the main motivation of this work, like what we are doing with this MEMS. And next slide, just like technical summary of this. For the first time, again, we're building a network of MEMS. If you're familiar with MEMS, especially the accelerometer that's presented in the slide, usually the MEMS will be one beam. We call it I-beam. And that I-beam will move when you apply acceleration. But for the first time, we're building a network of those I-beams that are interacting with each other. And we engineer them in the sense that each movement of those beams will simulate a neuron in typical machine learning. So when they move, because of the applied acceleration, also they do machine learning on the fly. So you're getting 2 in 1. It's been patent technology. Now we work into license commercialization, and being funded by multiple federal funding sources like NSF, Department of Energy, and IRBA funding. So now it's kind of the inspiration. So if you watch the video, we talk about the inspiration from NSEC that they do sensing computing. But also, and I still give credit to our brain. The computing in the MEMS was inspired by the brain, our brain, like the computing, because there's two concepts: sensing computing, inspired by the insect, and the computer itself inspired by our brain. I'm sure most of you know, but I just want to give some history here. In 1963, those two scientists, for the first time, they modeled the behavior of a neuron in our brain. And you'd be surprised how complex is that. Like only one single neuron in our brain, 4 highly coupled differential equation. And now think about machine learning nowadays. If you want to build a machine learning from 5 neurons, think about how complex is that equation to do typical machine learning. That's why, by the way, we call them artificial neural network. Because that's exactly the way our brain works. But you know, scientists are always smart. So especially in neuroscience, they found if you try to simulate those equations, you end up by those, they call them spiking for the neuron. What neuroscience found is what really matters is not the shape of the spike. It's the rate of the spiking. Are you spiking too much or less? And this rating spike is related to our behavior and learning. So all I'm trying to say, you don't need to simulate all those equations to do machine learning. If you can capture this rate of spike, you should be good enough. And that's what they did. They simplify all those 4 highly nonlinear coupled equations by a single equation, differential equation, linear differential equation. And I'm sure it starts getting closer to the machine learning we are familiar with. But the only difference you might not aware of, the first machine learning equation, they were differential equation. They involved differential equation with time. Yes, they were. And yeah, they have the sigmoid function. But you know, I was back in computer science. They don't like to do differential equation in computers, right? Imagine you have a network of 1,000 neurons. How you can solve all those coupled, even though one equation by neuron. So we end up by doing the difference equation, right? So that's a recurrent network where you simplify, you take the concept of time and start using a difference equation to do the machine learning. So this schematic kind of compare, if you look at the red line here, this is the original equation to describe the neuron, the rate of change of the spiking. We call it continuous time recurrent network. And it's merely adding the time to the equation. If you ignore that, you start talking about difference equation, you end up by the typical RNN. And I know there's a variation like long-term short memory, there's a transformer. But this is kind of the building block of those, if you ignore the red line. Now, what we are losing by doing so? It was hard for me to look in the literature to find 2 examples to compare somebody using the theta RNN, which is, by the way, is not famous. If I ask you, anybody hear about the theta RNN before? Continuous time recurrent network. See how science is a little bit biased, because it's very hard to solve with the computer. Nobody talk about it. Digital computers are good doing difference equation. And now everyone familiar with the recurrent network. But if you go back in the 90s and the 80s, continuous time is the first way to describe the neuron. Now, why I'm really stressing on this? I found very few papers about using theta RNN. Somehow they managed to solve those differential equations using a computer. For almost the same example, I can't do apple to apple, like the same example. It took me a lot of time to find like the most close to example. This reference, they try to classify hand gesture by RNN. They end up using 128 neuron, whereas that guy, only 4 theta RNN. Even I can argue it's more complex, right? You see, there's more complex shape to this. Here's kind of up and down, but here you can see more complexity. Only 4 theta RNN were enough. Why is that? Again, the equation of the theta RNN has other dimension with time that add more complexity to the neuron to capture more behavior. Yes, you can argue you need more to train it, but at the end of the day, once you train it, it will be better than RNN. So the reason I'm drilling in this more and more, because MEMS devices are structured. When you apply acceleration, by the way, they move. And their motion can be also described by differential equation. Believe it or not, there's a lot of kind of assumption here. I want to spend time there. Some engineering for the structure, how I want to design our MEMS. At the end of the day, believe me, we were able to match the MEMS equation to be similar to the theta RNN equation. Why do you think this is important? Why this is big? Because now when the MEMS vibrate, the vibration itself is the solution for the differential equation. So for the first time, you don't need a computer to solve a neuron, a complex neuron equation, if that makes sense. As long as you can monitor the motion of the MEMS, which is kind of trivial now. You know, your iPhone has 12 sensor of MEMS. They know how to do it, capacitor sensor and all that. Once you measure that, you are solving that differential equation without a computer. So the next step is, and I keep repeating this because this is very important, the other fact is this MEMS also is a sensor. It responds back to the measurement. So now for the first time, measurement, computing having the same time, the same spot, the same physical layer. There's no separation between those 2 worlds that's being defined by the industry. By the way, the Venus and Mars, this was inspired. I attended a few years ago. It was Hilton Head conference. A vice president from a leading company, he came to talk about sensing computing, and he brought those. Sensing is from Mars, Venus from computing. We never get them together. We can get them close. We never get them together. So I believe we're almost getting them together here with this approach. So now the natural step is once you figure out one MEMS, can you put them together to form a network that do machine learning and sensing? And that's what we did. So the first application we did with NSF funding, we, for the first time, built this neural network. We designed it to sense acceleration. The same time, those MEMS, they talk to each other in mechanical domain, do machine learning computing. And we picked up one of the common applications. If you talk about wearable device, one thing you're really interested to classify from the acceleration measurement, if somebody's walking, sitting, standing, so you can do some information with that wearable device. So let's say, let's do that. So we offline train this model. We build a model for our network. We train it, and then we plug the weights back. And by the way, the weights is very straightforward. There's a voltage. So those MEMS, if you're familiar, anybody familiar with the COM drive MEMS? Yes, one. Yeah, so the COM drive MEMS, they generate capacitance. You apply voltage, and based on the applied voltage, there will be more or less movement. So we think about those COM drive as a weight. So this is kind of an analogy between a MEMS network and a typical machine learning. Each MEMS is resemble the equation of the MEMS, the neuron. Those fingers are the coupling, are the weights between the MEMS network. And those can simply adjust by a voltage. So you train, you find a voltage, you plug it back, it does computing. And the big thing, again, it does this with a fraction of very small power. Actually, we show by calculation, we can run this classification from a single charge from wearable device for 10 years. So imagine that. Like right now, you need to charge your Apple Watch each, honestly Apple, just general wearable device, I don't want to be specific, each day. With this one technology, if you get mature enough, you can run your device, at least for machine learning application. I'm not saying this will replace the display or the lighting, all that. At least for those machine learning applications where you need to do something. And now you can see there's a lot. There's a lot push medical and all that to do diagnostic in the wearable device. But you cannot push more there. Machine learning, they are very expensive. I mean, in terms of power. They need a lot of power. And the bottleneck between the sensor and computing will add more to it. But with this technology now, we can do both at the same time. And again, think about this latency, like this sampling. All is gone. Everything is done at the same hardware. You eliminate all those problems. Now, other project I'm proud of, led by GE and funded by IARPA, we said, can we take this to the next level? The other advantage, it's all win-win, by the way. Like, you think about it, like, usually in life, you have solution, you have problem. But this one, I'm still trying to find where kind of major problem. The other advantage doing this in the analog domain is now you can do training also online. Like if you can run, this is very fast. And this is, by the way, real time. Your MEMS is vibrating real time. You can collect data real time. So with GE help, we built the first MEMS network that can be trained online. I remember in the final day, they come to evaluate the project. So in this network, we moved from 3 to 5 MEMS. Everything is running fine. The problem was green, you have a noisy signal. Very typical textbook problem with machine learning. And you want to recover the truth, the ground truth signal. You pass through the MEMS network, automatically train for the right gains, and then recover the signal. Even we try to make it complex by the ground truth now is no longer one frequency, multi-frequency, still did the job. Now remember, he came here, he unplugged one of those MEMS. So now the network fall down from 5 to 4. In a typical machine learning, that's a big change, right? You need to retrain everything. It just in a few minutes, it recover itself, online training, find the right train for the right weights, and recover the whole signal. So that shows like what the potential for this. Low power, simultaneous sensing computing, eliminating the signal processing, sampling, on top of that, enabling online training. And to give you some perspective, how powerful is that? The same exact problem, we use a digital computer with Python code, and we use a supercomputer. You can argue with this. I'm not expert with computer, but with 20 core, you can consider it to be a supercomputer, right? It took a supercomputer to do the training 15 hours, where this online training by analog training, only 10 minutes. And the amount of power that supercomputer needs is vast. Like you talk about 600 watt compared to 2 watt. And again, this is proof of concept. A lot of structure we add here, just demonstration. If you strip those out, you just do only MEMS, this will be fraction of what. But just for demo, for flexibility to adjust things, we make it still kind of circuit-like. But eventually, this go as purely MEMS, does computing and sensing. So what's next? So the other application we're targeting now, like this, as the video mentioned, is bridges. In the US, they are failing. For the first time in 2018, the number of the bridge labeled to be fair are more than the good one. And fair, by the way, is one stage before the poor, which means you have a problem with the bridge. And yet, only out of almost 500,000 bridges, only hundreds being monitored. Why? Because to monitor them, you need to put those sensors different places. You run cable for power. You transmit the data, all this headache. So they don't afford that. With this technology now, we can just throw those MEMS with one single charge. They can last for many years. But we can acknowledge now the computing might need more complex, because this is not like a simple classification. So now we start talking about multi-dimension of network. We start by 3, with G to move 5. Now we'll talk about 20 MEMS, 30, 40. So we start looking about topology, how we arrange those MEMS. So you can capture more dynamics, more computing, more power. So this is kind of sample design. We call them deep MEMS network, to an analogy to the deep network that we are familiar with computer. The other project, non-disclosed funding, I just got like last week, is to use for 3D printer, additive manufacturing. What we found is, 3D printer now is being used almost everywhere. But they have a major challenge. Their challenge is to do a job, most of the time it takes a day or so to print the product for yourself. The problem with that is if something happened during the process, you have to wait for the whole day and then stop the machine and know there's a problem with it. A lot of people, they try to do this online monitoring, but the problem, those failure mode happen at high frequency. They use acoustic sound and all that. You talk about 100 kilohertz and even mega kilohertz. You cannot afford to collect all gigabyte data and process it online with even a supercomputer. But with this technology now, you can online processing the data as it comes, and then declare if there's a fault and stop the machine. So this is kind of one application. We're really starting this project this month. Other project, I talked with some faculty at the MIT might be interested in this, flying robot. So flying insect, flying robot, we come back to insect. We love insect for every reason. But a major problem, a lot of people, they try to do those insects, but the major problem with those insects is the weight. They have a lot of restriction about the weight. They cannot afford to put a microprocessor with a sensor. So with this technology we're talking about, we can shrink the sensor and computer to be one structure that can be planted to the insect and does computing, and move it from open loop to closed loop for the first time. So they can add some autonomy to those robots. So they can be more smarter than being open loop, or as been taught today that they use camera, high-speed camera, and then feedback. So we can just do it import of this micro robot. So this is actually walking. There's a flying robot. There's different application. Like I did some simulation with a walking, but also the same thing can apply for a flying robot. Now, honestly, my best kind of not yet explored, which I think very open for collaboration and investigation, is this. We live in a world where one measurement is not enough. You hear this a lot of time, model sensing, model sensing. I'll just give you an example from my research. When I start my research, I start not fundamental, just do application. My first research was to model thermal comfort of a human. I underestimate how complex is this subject. And then I realized, to give a status of somebody's his cold or hot, you need a lot of measurement. The key one is temperature, as you might think, humidity of the room, and your activity. If you're running, it's different than you're sitting. So at the end of the day, at least if you just narrow down this temperature, humidity, and acceleration, because acceleration is kind of surrogate for the activity level. Now the irony, there's a big irony. Again, separating sensing from computing creates a lot of problem for us. The irony in this model sensing approach is, if you're familiar with sensor, if you've been working with a company or contact to get some code, for example, when I get an accelerometer for my job, I do flying robot, I want to get accelerometer. In the data sheet, they would say how much this acceleration will affect by temperature. And believe me, they spend a lot of money to compensate that sensor that can only measure acceleration, right? To make it selective, selectivity. They try to make this sensor, because think, by the way, MEMS, the same MEMS, it's all about how you design it. It can be sensitive to acceleration, can be sensitive to temperature. Like you have 12 MEMS in your, or more in your iPhone. It's the same structure, kind of, but how to optimize it to be more sensitive to acceleration than temperature. But again, you cannot get rid of that. You design for acceleration, temperature will affect it. And you spend a lot of research, a lot of circuit to cancel this. The irony here is, especially for those model sensing application, you want them together again. So you spend a lot of effort, separate them, and now when you do machine learning, you want them to put them together, right? It's a very big irony, right? Now, it's irony because nobody think about this sensing computing to be the same time, the same place. Now think about this work I talked about, when you start doing sensing computing at the same place, right? Now you design your system or your sensor purposely to be affected by acceleration, by temperature, by humidity, whatever you want, and then you train it such that to give you the output you want. I talked about the thermal comfort. I don't care what temperature is. I care about, am I comfortable or not? So I train my sensor, network of sensors, to give me that output. Now I don't need to worry about the selectivity, which a lot of problems cause in our industry. Believe me, like I've been in contact with a leading industry for 6 years or more. Each time I contact them, do you have a problem to solve for you? Yes. Can you solve me how to compensate temperature from the acceleration? And then I ask, what application you want? I want to have it for where I need temperature. So it's kind of really, the way he talked this, I mean, because that's the way people separate sensing from computing. And that's why it's keep happening and costing a lot of people money to investigate that. But if you think in this approach where you can do sensing computing the same place, the same layer, the same physical layer, then you can train it to give you what you want. You don't need to worry about being selected for each measurement by itself. So I think this is not explored domain yet, but I think there's a lot of potential for this, especially for applications that required more than measurement. You know, during COVID time, one thing I was selling with this is, you know, body temperature, the skin temperature is different than the body temperature. So I think there's a Europe company, they invent an accelerometer with temperature and multiple sensors. With machine learning, they were able to estimate the actual true temperature, body temperature, the inside, which is more representative for the actual body temperature. The same argument. They spend a lot of hardware how to get the acceleration by itself, temperature by itself, and then do machine learning in a microprocessor to do the true body temperature. Believe me, with this approach, you only need one MEMS that can respond to all those measurements, do machine learning in the MEMS structure, and then give you the output you want. So again, what's next? So the applications are vast. So now I'm kind of thinking about, like, this is kind of multidisciplinary domain, research domain, that a lot of people from our field can be involved. You know, not only MEMS. You're talking about computer science. You could talk about computer engineering. You could talk about neuroscience, you know, because there's a lot of inspiration from neuroscience. So I'm now floating the idea, like, there should be like a center around this, like where people decide together on how we can solve this problem. This is a big challenge. It's been for many years. The domain for computing is completely separate from sensor. If you work in the industry, by the way, like sensor guys, they don't talk with machine learning. They are completely separated. Give me the data, I'll do machine learning. The sensor, give me the spec you want, I'll do it with my sensor. They don't talk to each other, and that's create a lot of problem. We need to kind of bridge that gap, and you can see how much benefit we can gain from that. So it's a roadmap. You know, we always start with roadmap. If you're a student, PhD, I'm sure you have a roadmap, what you milestone want to do to finish your PhD. Same thing here, believe me, we do the same thing. So when I started this idea 5 years ago, my roadmap was to put some patent application, get some funding, which I feel I'm good with that, engage people, national lab, industry, and now to talk about a center. So I think that's why kind of my vision here, how to move this forward. It's not one single effort, it has to be multidisciplinary, multi-university team to move this up. So the video explained more about this insect inspiration. This kind of some of the application that this can go with. There's a lot here, but, and anybody hear about the concept reservoir computing? Anybody? Yes, same thing can be done with MEMS. If you guys familiar with reservoir computing, the main condition you need to have a very complex physical system. MEMS has it, by the way. It has very strong nonlinear dynamics. It can be a whole lecture by itself, but we show with single MEMS, with reservoir computing, we can do also the big advantage compared to typical reservoir computing. You can blend sensing with computing together. So you gain all that thing, like the sampling and all that. So the same thing we did with the reservoir computing. I think there's a lot to cover here, but I'll leave time for questions and answers. And thank you for listening.
Thank you for your presentation, and now we open the floor for questions from the audience. Okay.
Thanks very much for your talk. Is the fabrication reliable enough that every chip can be given the same model after training, or do you need to individually train every single chip?
Yes, good question. So first of all, speak about fabrication. I didn't talk much about it, but the good thing about this approach, we're not inventing new way. I mean, doing accelerometer is so kind of solid enough that we have in our iPhone. So the only thing we're doing is replicating those MEMS. So we're borrowing the existing literature, like 30 years of improving fabrication MEMS. Now, the second question, yeah, even there'll be some fabrication tolerance that could produce some error, right, from the machine learning. So that's why we think this online training that led by GE can handle a lot of those issues. Like literally, we took one MEMS out, whole neuron, not even changing the structure. The whole neuron is out. You're shrinking down your size from 5 to 4, somehow still able to train. But yeah, the vision for this one, the online training, since this is analog fashion, the online training will be the saver for us in this regard. Yep. Good question, though. Thank you.
Anybody else? Okay.
Yes.
So I just have a quick question about the readout. Yes. So you said that with one charge, then this thing can last for a very long time.
Yes.
But eventually, how do you take out the information?
Good
you still
question.
rely on electronics, right?
Good question. So far, again, we're relying, very good question. For this classification, we rely on the binary classification. We'd like to detect activity, which can be coded as a binary. Like if you use 2-bit, then you can do a 4 classification, like walking, standing. And those MEMS are switches, right? So for this specific example, what we did is, so this MEMS, this I-beam, can close a switch with this pad. This the same thing here, and the middle one can close here and there. So we can train it such that, for example, somebody's walking, this I-beam will close, and this will be binary 0 or 1, if that makes sense. So you don't need even to convey, especially for classification. You don't need to read the capacitance. You can rely on the switching, because MEMS is a switch. And you think about each switch is a binary, and you can train this network such that it gives us all the combination we want, if that makes sense. Especially for, when I said 5 years, this is based on this binary classification. It's just like a switch, does not need any power. But yeah, if you want to read out like the GE application, that's why we still consume some power. Because in this case, it's kind of continuous. You want to generate a signal, capacitance measurement, then yes, you want to, at least for the output, you need to kind of read out that. But still, we can argue we are way much better than typical computer to do so. Yeah. Good question. Thank you.
Great. Thank you for the talk. So often in these neural network applications, the fan out and the integration is as limiting as like the neurons themselves. I totally get MEMS as the neurons. It totally makes sense. But in terms of, in your approach, are you doing this fan out and integration on the MEMS chip? Or are you still sending that data to another CMOS chip, then bringing it back on to the MEMS neurons?
Yeah, so this application is more about doing all at the same time. So think about, again, the acceleration will apply to this structure. The structure will move, and then it will talk to each other mechanically and produce the output. So there's no, I think, coming out our end. It's just like, and that's kind of the beauty of this. Like we are really moving the computer to the sensor level, where, when you do typical machine learning, you don't care about how you get the measurement, the input, and then you do machine learning. This one, the whole structure is subject to the input. In this case, it's acceleration. Could be temperature. And then we engineer them, we train them so they respond to that acceleration and then produce the output we want. Yeah.
So you're limited only in like neighbors talking to each other?
Exactly. So the one thing we talked about, like that's, I talked with some faculty in MIT, how to shrink the size, the nano. Those are micro. Shrink it to the nano, then we can add more MEMS, right? And the other thing I try to sell when I talk with funding agencies, the thing I said at the beginning, the fact we're doing differential equation, we having head start with compared to typical machine learning. We need less neuron to solve problem compared to typical RNN. Yep. So between this and that, we can propose something better than what exists now. Very good question. Thank you.
Thank you for the good talk. So after the training, like, do you store those information in the memory, or like, are you like,
Yeah, good question. So far we kind of more application dependent. So when we demonstrate, like we publish this in Nature Communication Engineering, like the same hardware, we just like typically DC voltage. Like the weights are nothing but DC voltage. So if you want to like think about Apple Watch application, you want to just detect the activity, you just always send the same voltage, DC. And those are capacitive, they don't consume power. So this voltage just like to hold the plate. Now for the same paper, we show if you change this bias, we can move to completely different application. Yeah, so it's kind of as simple as, yes, if you want to like kind of more reconfigurable network, then you need only to store the voltage for each of those weights. Yep, that's the minimum you need for that, the maximum you need. Yep.
Okay, thank you.
Yep. But everything else is done, like that's kind of the other inspiration for human brain. We don't store information. I mean, the processing in our brain happens instantaneously. There's no need to store memory. Like that's kind of the major limitation of current digital computing. They separate the memory from the computing. If you do it in analog fashion, everything happens at the same time. Yeah.
Thank you so much. This might not have an answer either, but it's more like you showed the equations for a neural network, and you showed that you can replicate those equations very similar.
Yes.
But what if you have something more complex? It's still partial differential equation, maybe a solution of a fluid dynamics problem, which takes a lot of computational time. Is this something that we can do with MEMS?
Yeah, so like honestly, the more I learn about like this artificial intelligence, the more I realize it's not like you have to really match a specific equation. You know, if you read about this reservoir computing, this is the extreme to me. Like the one who's familiar with reservoir computing, literally they say just bring very complex nonlinear equation and you're good. Like just like that, that's kind of the extreme they get. Like, and then by the way, if you guys are familiar with this, you can talk more. You only need to train the output layer. You don't need even to train the weights among themselves. You can start with random weights, just take the output of this reservoir computing and do the training. So all I'm trying to say, you don't need exactly to match the equation, but with this reservoir computing, they claim they can solve almost any problem in the world by this virtue of reservoir computing theory. Yeah. Yeah.
Thank you very much for the interesting talk, very interesting work. So I'm just gonna maybe throw some food for thought.
Sure.
So the information that's being fed into this computing system is what's being sensed. So what if we have a scenario where we need also to couple with that sensed information that comes from a different source? So like, for example, this comfort, you want temperature, humidity, and maybe acceleration. How about my mood today? Right?
Oh, yeah.
You can't really sense that.
Yeah, yeah.
Right? So have you thought about this? How can you couple that information into this computing system?
That's a very good question, actually. As you mentioned, it's like a food of thought, but the easy way I can think about it, this will come as an input voltage to the MEMS. Because the MEMS at the end can also receive voltage. So wherever that mode thing can be sensed by other sensor, this will come as an input analog voltage that to the MEMS. And then you can train to the way you want to receive that input voltage. Yeah. And that's the big thing about MEMS. Yeah, they're excited by voltage. And anything in the world, you can at the end of the day convert a voltage that comes as input to the MEMS.
Very nice. Yeah. One last question. Yeah. What's your vision on the scalability of these MEMS networks?
Yep. So my vision is like what you guys can offer here. I have a lot of good talk with faculty at MIT. They talk about dealing with nano device. Because, you know, I don't have fab in my university. I rely UT Dallas. The maximum or the best they can do in micro scale. But if you can scale those to the nano scale, you know, now you can think about having 1,000 maybe in wafer, in one chip, you know what I'm saying? It's all about that, like how much you can scale the MEMS device. Yeah.
Thank you very much.
Thank you.
Anybody else? Okay.
Yeah.
Well,
Just one more question. So regarding the time constant,
Yes.
so if I have a network of components and each component has very short time constant in its behavior, how can this network, which doesn't have memory, can respond to a signal that lasts for 1 second?
Good.
For the sit and stand.
Very good question. Yeah, so, MEMS, if you're familiar with natural frequency, is square root K over M. So there's MEMS like I have one in the labs, I think the natural frequency around 100 hertz. It's not still 1 second, but you can go to megahertz. So the MEMS itself, by changing the dimension, the thickness, the length, you can play with that range of frequency, like the sampling time. And actually, this is one of the outcomes of our project with GE, where even the same MEMS itself, I don't want to go in much detail there, but if you apply a voltage, just DC voltage for, who's familiar with the capacitive MEMS? If you apply voltage, it will soften the MEMS. So the natural frequency will go down till pull in, which is literally 0 frequency to almost wherever you start. Like you start with 1 kilohertz. You can tune the same MEMS, exact MEMS, by applying voltage. You can change the frequency in the fly. So one thing we talked about is even training for the first time. Even if you look at the literature, CTRNN, which is a very good question you brought here. When they do the CTRNN, the only few do it, they assume time constant to be fixed or randomly select different values. With this MEMS, the fact it's a physical device, and you can tune it with the voltage, you can make this part of the training. The time constant, so you can start by all MEMS have the same natural frequency, have the same time response. While doing the training, you figure out this multi-domain or multi-scalar signal. It will end up at the end, beside the weights, that's kind of the work we're doing now. Beside the weights, also the time constant for each MEMS will end up be different. And it's very easy to change the time constant for each MEMS by just changing the bias voltage. That makes sense?
Yes.
Yeah.
But how does motivate you to go to nanoscale?
Yep. So nanoscale, the major drive for this is the size. Right?
Yeah.
I know when you go, very good point as well, we go with high frequency. Yeah, exactly. Right? So it's a trade-off, right? So it's like some application, like you need, size is issue. But honestly, to me, if you ask me, when you go to nano, it's more about high frequency application. You know what I'm saying? But if we look for, as you mentioned, the gate and all that, I think we're good with this. For this frequency range.
Thank you.
Yeah. Thank you. How do you guys like the video? Took us 2 days. And this is a good example for a good grad student. I brought him. I brought him in my team. Let me show. It's recorded, so he'll get some acknowledgement here. They sold him for me as the guy who do BCB. And then I asked him one time to do a paper, like a figure from my paper. He said he was not busy, so was doing some stuff. And he did it. And then I started realizing he's hiding something. And then I told him I have a presentation, this guy. I have a presentation to MIT. Can you help me to do a small video? And interesting enough, he's the newest to my team, so he didn't know much about this MEMS computing. And he came after one day with this initial plan. I said, wow, I've been working this for 8 years. I never understood it as your video. So with some touch, he was able to finish it in 2 days. Yeah, so it's really interesting about how much you might have with your grad students. Not only research, but the other skill they can bring to this research. Really, it amazes you. And that makes sense. Any more questions?
I mean, there have been plenty of questions, but maybe perhaps somebody would like to ask some more.
Even a joke. Yeah, I need to ask. My brother, right? This is a good story. My brother, he gets PhD in gaming. He was surprised from Utah. He said, "What software he did?" The same question. I told him, "I don't know. I know at least he used for the audio, he used the Microsoft automated voice, but I don't know about the software." Yeah. And other joke here. Again, I've been doing this for the last 5 years or so. In our university, they have support. Like if you want to take this commercialization and all that. I've been sending presentation slide and nobody replied back. I swear to God, I sent this one 5 minutes after. Hey, Fadi, I want to meet with you. Same information for the last 5 years, nothing changed. It's just how to present the information. I thought, I'm from academia. I know I work for industry, but I thought, hey, read this paper, research paper. I don't think they read it, or they even understand. I mean, I don't want to say that, but they read it carefully. And they never reply for a year or so. I sent this immediately. I can show the email 5 minutes after. Hey, Fadi, do you have time this week to talk? So again, the way to present your work is also really a key. Yeah.
Let's thank the speaker once more.
Thank you.
Thank you. See you in the next seminar. Thank you.